Hello, I'm Mark Unkefer, Executive Director of the Fiber Optic Sensing Association, and welcome to our webinar. We're privileged to have OptaSense's Chris Minto as a presenter. And Chris has been really one of the mainstays of the association from the very beginning, served as our first technology chairman, and I think all the chairs who came after him will attest that he set a very high bar of excellence, and also great at engaging and recruiting people to get involved. So thank you, Chris, for all of that. But we're now focused today on integrated strain, temperature, and passive seismic sensing. Chris, we look forward to your presentation.
Thank you, Mark, for the introduction and for those kind words. Good morning, good afternoon, and maybe good evening. Hello to everyone. Thanks for taking the time to come and visit this webinar. Really pleased to be back presenting a FOSA webinar. Our last webinar was September 2020. As Mark says, we're going to be looking at the practical benefits and field data from integrating strain, temperature, and acoustics in a single device. What can that do for you as asset owners? We'll look at a few different projects that we've been exploiting this approach on, and we'll look at the results. The talk itself follows on from my last talk, which was September 2020, where I presented a talk on new paradigms and new opportunities for fiber optic sensing. Essentially, our goal then in 2020 was trying to extend the remit of DAS technology, distributed acoustic sensing, based on Rayleigh backscatter, which is the little bit of science behind it, extending it out of acoustics and into the regime of looking at strain and temperature, because the technology is certainly applicable in those areas. And at the same talk, I also presented on expanding boundaries through intelligent use of glass and intelligent cable design to open up new doors. And really this talk goes back to that and says, well, what have we done since then? Since we've burst open some of these new paradigms, let's see what we can do with it. So if you're interested in the science behind it all, that's in this earlier talk that's still available on the FOSA YouTube channel. So first part of the talk, I'm just going to give you a little bit of historic coverage on how we can measure temperature and strain in this class of device, a very simple overview, and then we'll go and start to look at the project data. So it's really very simple, and now this sort of class of distributed fiber optic sensing is becoming much more mainstream. Maybe not quite global coverage yet, but we see more and more use cases appearing, and they're all based on the same fundamentals of technology. Time for a quick animation here. So that's the basis of the technology. It's really very simple. We take a very short pulse of light. This is my green light. It's maybe tens to hundreds of nanometers long, very, very small indeed, but relatively powerful. We launch it into a fiber optic cable and then a single strand. And what we are looking at is the echo of that light from the glass itself. And in that respect, it's kind of analogous to a radar or a sonar system. We send out a short interrogation pulse and we listen to this long echo. The echo comes from the interaction of the pulse with the glass itself. It's a backscatter process, and there's a few different backscatter processes. We use one called Rayleigh backscatter. The details are not important at this stage. But fundamentally, what is important is what this backscatter process conveys about the nature of the glass itself. And I'll cover that on the next slide. But as this process occurs, it occurs at the speed of light. This pulse of light launches down this fiber until a point where we're not getting any useful energy back. And that's somewhere of the order of 60 miles or about 100 kilometers, depending on the quality of the glass. It can be a little bit more, it can be a little bit less. But that's about the sort of typical maximum that we would operate out to. If you're doing that, you can repeat that process about 1,000 times a second, 1 kilohertz. If you make the fiber half the length, you can do that process at twice the speed. So the shorter the fiber gets, The quicker you can carry out this process, and thereby revealing more in terms of information. And what I mean by that is the acoustic content. But let's just see very briefly in the next slide how we get that. This is the only slide with the detailed physics in it. So here's our interrogation process. We have this short pulse of light in green that's listed as being quite large, and that's traveling down the fiber. And we're looking at the backscatter process, the echo of this pulse from the glass itself, from its interaction with the molecules of the glass. And this is a key point in terms of how sensitive this technology is. We're using individual pulses of light, which are very, very short, and we're scattering from molecules of glass, which are very, very small. And the way we do this is to make an interference pattern. And you see a nice visual example of an interference pattern. There's more in the previous talk I referred to earlier. But essentially, what we're doing is blowing up so we can see it, individual lengths of wavelengths of light. We may, for example, make this interference by having one or more pulses in the glass, or we may take this pulse and refer it back to a standard pulse that we keep in the box. But essentially, this is what we're doing. We've got the width of our nominal pulse as we send it into the glass. It's creating backscatter as it passes through this glass, which is coming back towards us. And so what happens, the key question is, what happens if I stretch this glass? Or what happens if I heat it up so it expands? Well, that nominal length becomes a little bit bigger. The reverse happens if I squeeze the glass and compress it, or if I cool it down. And acoustics is just this happening very, very quickly. It's vibrating in and out in sympathy with the acoustics, the acoustic field it's sitting in. And because we're working with small pulses of light, what we can measure at each time we take this measurement, at each point along the glass, is essentially the difference in length of the part of the glass we're interrogating compared to our standard. And we can measure that in terms of individual wavelengths of light. And so what does that correspond to? So typically, we'll maybe work in an interrogation pulse that we're working in meters long in the glass, 5 to 10 meters worth of glass that we're lighting up at any particular point. And we're looking at microscopic changes that are of the order of wavelengths of light in the glass. So the measurement we use, last bit of physics, bit of maths here, the measurement we use is radians. So there's about 60 degrees in a circle. That would be 1 radian. There's 2 pi radians, which is 6 in a bit. That takes you all the way through 360 degrees. So we're measuring, that sort of wavelength of light. This is growing or shrinking by 1 radian corresponds to about 15 parts in 10 to the 9. You get tiny, tiny strains. The breaking strain is typically about 1%. We're talking 6 orders of magnitude smaller than that. Or alternatively, if we were to heat it up, 1 radian is about 1,000th of a degree, Kelvin or centigrade. Sorry for the Fahrenheit guys. These are really small numbers, but they're not the noise floor. A radian is quite a big measurement for us to take. Our noise floors are about 3 orders of magnitude lower than that. So we're down at really fundamental movement that's taking place in the glass itself. That's why we can resolve acoustics, we can resolve tiny, tiny strains in the glass, and we can resolve very small temperature changes in the glass. Whether you can access them, whether the temperature is changing so much that you can't see the strain is another matter. We're going to come to that later in the talk. But the only key point that you should take from this is that with this class of instrument, we can take all 3 of those measurements essentially out at the same time. The temperature and the strain might be coupled together, so we can do some tricks to separate them. But at every measurement we take, which is thousands of times a second, we're getting very precise temperature, coupled with strain and acoustics. And the real part, the interesting part, is what can we then go and do with that? So let's move on to look at what we do. So In OptaSense, our mainstay of our work has been, since we started, distributed acoustic sensing. And so that's forgetting for the moment about the temperature and strain aspects, concentrating on the acoustics. What's the sound like at every point along this fiber? And we've got a whole host of different detection modules. So it's a great party trick to have 10,000 microphones spread out along a fiber optic cable. That's what we give you. But who's going to listen to them? So the computer has to listen to them. The computer has to listen for the patterns of sound, whether it's a train passing and going over a broken rail, whether it's the sound of footsteps of someone coming up to a fence, and so on. And we've got individual detectors for all of these. That's the mainstay of our business. There's plenty of places that's covered, so I'm not going to concentrate too much on this. We'll bring up some examples as we go through. What I'm more interested in today is some of the more advanced application areas where we can pool capability together. I mentioned that the strain and temperature might well be coupled. Indeed, how can you tell that a 1 radian strain comes from cooling the glass or from heating it? Fundamentally, you can't. If all you've got is one strand of glass, you can't. So instead, we look to intelligent cable design. If we've got a segment of a cable that has 2 passes of fiber in it, if one of them is sensitive to temperature and acoustics and the other is sensitive to temperature and strain and acoustics, we can separate the 2 out by subtracting one from another. And we can do this with the design of cables with loose tubes, which are not sensitive to strain, and tight buffered cables that are in the same cable. And there's a little illustration here of how we do that. Green is the actual temperature recorded on another sensor, just so to make sure we're not cheating. Red is showing us the output from the loose tube. We've separated out the acoustics so that we're not worried about that. We're just looking at this very low frequency temperature trace. And the parallel trace from our tight buffered cable is shown here in blue. It follows largely the same format. You see here my y-axis is in radians because I haven't separated them yet, but there's some differences. It doesn't exactly follow. When you subtract one from the other, we can then resolve the temperature separately from the strain. And here now on my y-axis on the left, I've got temperature in degrees, and on the axis on the right, our red axis is strain in microstrain. So we've got a calibrated and understood performance in the cable, and we're using the combined performance of one fiber, subtracting it from another to resolve these 2 different components. More as I mentioned in the previous talk from September 20 on that. What we're going to look at today now is some of the results. So first of 3 examples. In the first example is the results from an academic partnership with OptaSense, the British Geological Survey, and University College Dublin, looking at strain and seismic monitoring from a landslide-prone hillside. After that, we're going to look at a couple of industrial applications as well. We've used this project, we've been part of it over the last couple of years, and we've used this really as a test bed for these new techniques, working with the scientists to try and probe the activities that are taking place within the hillside, and to understand more, to be able to look at the onset of landslide activities, look to know whether we could consider the hillside to be at risk of slipping before it actually happens. And that's one of the keys. And the applications of this are quite broad in terms of earthen structures, things like tailing dams, reservoirs, levees. If we can look into them and be able to understand the structure and strength of that structure, whether it's going to be prone to deterioration, we can do a lot better than just sitting and waiting for the detection of a failure. So that's what we're all about. So where is it? So this is Holland Hill, which is the National Landslide Laboratory in the UK. It's operated by the British Geological Survey, who are the British equivalent of the USGS. And it's a particular structure hill. It's located in North Yorkshire, which is most of the way through England, almost all the way to Scotland. Structure of the hill is as follows. It's a multi-component structure. At the main bottom part of the hill, we've got a stiff sandstone formation. And at the top, we've got, again, similar, but not quite the same, stiff dogger formation. The part that causes the interest is this big mudstone formation. And the names are kind of a clue to this, the mudstone formation. It doesn't sound terribly stiff. And what happens essentially is when the sandwich that we've got of two stiff parts of rock with this mudstone in the middle, when it starts to get wet, and particularly when it gets to about 45% moisture content, it loses all of its structural stability, and the jam sandwich squeezes and the jam starts to come out the sides. And what we see is this actually happens. We'll show you in a couple of pictures in a minute. At the top, you get the jam starting to slide, to fall over itself, and then comes and vomits down the hillside over the sandstone formation. It's not a particularly fast operation, but it's nevertheless one that's visible over reasonably accelerated timescales, which is why it's great as a laboratory. It's also very heavily instrumented. So there's a little 3D view of the location. It's not the array itself, it's a little bit more complex than that. And down here is the farmhouse from where we operate our equipment. So here's a little view of it. Again, a little pictogram of our array. We run our a fiber that's, well, we still record data on it. It's not necessarily part of the experiment, but it does actually show us some interesting behavior along a farm track. And then we have a complex array that runs both up and down and across the hillside. You can see here where I've drawn on top of it in the light green a couple of the paths of fiber. And you can also see, this is obviously at the top of the hill, you can very clearly see where landslides have caused a slippage and a scarp to form. But also you see the structure of the hill here is quite chaotic and jumbled, caused by progressive slips year on year. And it's in the autumn. We're very lucky. Britain's a very wet place. It makes it an ideal landscape for this type of work. Looking down the hill from the top, we can see a couple of the other measurement facilities. There's a meteorological station, there's geophones and SAR reflectors, tiltometers, and other instrumentation dotted along the hillside. So here we're running our cable, we're coming in from the farmyard along the track, and then we're running up the hill, we run along the hill, and then up and down, so we're getting multiple passes. And then in this section in the middle, we have two passes. In that section, we've got that temperature and strain separation I was talking about, our Proteus 7 running up and down the hill in the middle, so we can see both components discretely. And everywhere else, we've got a tight buffered cable, so we're seeing strain overlaid with temperature. We're not trying to separate them. For what we're interested in here, it's generally focused on large strains. We're not trying to delve into the smallest numbers, although as you'll see, that resolution is particularly useful. So it's nice to separate them in one example, but we didn't need it separated everywhere. There's quite a few publications on this in the literature that we've done over the last couple of years, but this is one of the really nice sort of results. This looks at some of the behavior over the winter of 2020 into 2021, which is, as you'd expect in the UK, a wet winter. So here we're running from October, end of October on the left-hand side through to the end of January on the right-hand side. And these are our strain plots that are just being collected from this system. Again, acoustics for now, we can just pretend they're not there, although we are collecting them all the time. What we see is there's zero strain in the middle, and so we see some positive strains, some parts of the array delivering a positive strain, a general upwards trend, and some parts of the array delivering a general downwards trend. That's a negative strain, it's a compression. But superimposed upon that are some really significant jumps when clearly there's been a change in the conditions, and there's been a particular jump of significant strain, both positive and negative, which is very much indicative of movement taking place in the hillside. And these coincide with storms, winter storms that have been taking place in late December and early January. Storm Bella, Storm Christoph, and then on Boxing Day there was one that didn't quite get graded up to being a storm, but nonetheless there was a lot of rain came down. And so when we look at the distribution of those channels, and our channels are meters long, so we've got quite a lot of fine precision and granularity on the hillside, we find that the compressive elements are located roughly in the middle of the slope, and the elements that are in tension up in the top of the slope, really aligning well with the concept of the slope moving down. And so we can see events happening, but there's a little more than that, as we'll see. Overlaid in the background is some electrical resistance tomography. So this is a technique that the BGS use to probe the moisture content that's in the soil and try and work out, correlate to when these things happen. And this is just showing a percentage increase over the same period. And again, beautifully, the ERT results align very well with the areas that we see movement in. We'll come back to that in a minute. Same graph, same heavy rainfall, but now thinking about both the dynamic behavior, the high temporal and spatial resolution, because all of these bulk trends you could get from a typical strain sensor, a Brillouin-based strain sensor that averages its results as it goes. They're quite big strains. One of the beauties of using the Rayleigh backscatter and our Quantex system is that we, as well as having these sort of large bulk changes, we're getting results out at 1 hertz and sensitive to tiny changes in strain. And so I can take any one of these sections and blow them up and start to see some more information. Now, this isn't noise, it might look a bit noisy. What we're seeing here is a periodic increase and decrease in strain. Sorry, this is strain change in this plot. So an increase in strain and then a decrease. If we plot that out across the hillside, it starts to tell us some very new things indeed. And here I've gone from scales of thousands, a couple of thousand microstrains down to 1 microstrain, resolving over minutes rather than months. So here's the hillside laid out and looking at it in change in strain over change in time. So the differential quite often tells us a lot more than the absolutes. We can see a few things on here. We can see the diurnal temperature changes, because in the majority of this cable, we've not separated out strain and temperature, just in the middle. And in this section here, from about 1500 to 1650, you see we're not seeing these diurnal temperature variations. And that's because in this area, we've done this sort of strain and temperature separation. And so that helps us pick out what's temperature compared to what's strain. We can see the onset of a storm here with some very significant changes. It looks a little jumbled because think about my geometry. I'm going up and I'm going down the hill. This area here on the left is the farm track coming in. So that tends to perform all the same. So it doesn't work quite so well in this sort of 1D format. You really have to display it in 3D to get the best of it. But the part I'm really interested in here are what are these periodic things that are going on. And if we zoom in on these, this is the snip from earlier that we looked at, the prelude or the exit from a big shift in strain. What we find is we find the soil either, in different occasions, either building up to a failure or recovering from a failure. And this is a sort of stick-slip type operation. We can see that on the back of that storm on the 28th, I'm seeing these periodic changes, these little tiny slips of an order of, a thousandth of a microstrain per second happening, and then slowly increasing their period as the hill relaxes. Now, this is brand new geophysical information. If you're just putting out conventional instruments and averaging the performance over tens of minutes or potentially more in order to get to a good resolution of measurement, you're going to miss all of this. And this is why this has never been seen before. And the ability to point to these as an initial prelude into an event or looking at the exit from the event tells the scientists an awful lot about the structure of the soil and the physical properties. So that's great. That tells us something's just about to happen or something has happened. Industrially, well, that's not so good. You could go and look at it and tell about that. It's handy to know if remote areas have had some changes, and this is particularly useful for pipelines. But can we do better? Can we start to anticipate some of these and know whether we're building up problems for the future? And so this is where the seismic monitoring comes in. So I'm bringing the acoustics back in now to start to think about what they can go. So conventional seismic approach would be to go out there with an active source like a sledgehammer, hit the ground, put some geophones in the ground, look at how the sound spreads out. We can then do a process called multi-channel analysis of surface waves to look at the relationship between the spread of frequencies of that sound. So if there is a spread, the high frequencies will tend to be in the shallower parts of the soil and the lower frequencies will be in the deeper parts of the soil. And we can look at how they perform, what their velocities are, by just looking at how they arrive from the movement of the peaks of that sound energy as they come towards you. And then we can take what's known as a dispersion curve. We can invert that to move from frequency versus velocity at a point to look at change in velocity over depth. You could go then a step further and turn that into soil properties if you know enough about the soil to convert from speed of sound, which is a product of density and stiffness. If you've got one of those, you can get back to stiffness. And now we're talking mechanical properties of the soil. And so University College Dublin have been doing this at our experimental site. There's the array of geophones. That's how you go about doing this sort of process normally. You walk up and down with a sledgehammer. You hit it at various points along the hill, and you get these beautiful curves showing how that shock wave propagates through the soil, and then pull out your dispersion curves. Well, we've already got our acoustic arrays sitting in there doing the terrain and temperature analysis for us. So can we use them in the same way? Here are the results just from the active survey and the geophones. Apologies that these are on slightly different scales. But here I'm just showing that over a period of time, these things do change, and those changes correspond to changes in the physical properties of the soil. We can compare the geophone on the left here to the DAS on the right, the distributed acoustic sensor. So this is conventional geophone, that string of them that you saw. This is getting the same data out of our fiber optic sensor. It's not a perfect one-to-one match. We don't have the same access to some of the higher frequencies, but broadly, it's of the same shape. We see the same elements of dispersion, that sort of differences in speed of sound that occur due to the soil. And we can perform our own dispersion curves. And whilst, again, they're not a perfect one-to-one match, especially at the higher frequencies, the bulk behavior, especially at the lower frequencies, which corresponds to the deeper depths, is broadly correct. It's a reasonably good representation. So we could send someone out with a sledgehammer, but we've got one advantage up our sleeves. If you wanted to know how this performs day in, day out, you'd have a guy with a sledgehammer running up and down every day, and that doesn't sound efficient. So instead of getting all this sort of high quality data from a sledgehammer, we've got another ace up our sleeve, is that we're continuously monitoring. So we can trade a short, sharp, instant whack with a hammer for looking at the behavior of the array over an hour, over a day. We can suck in all that background noise and then create a virtual shot from it via some pretty cool maths. What we can evolve from that virtual passive data is our equivalent of what if we'd stuck all that together and it just came from a sledgehammer. And we can extract dispersion curves in the same way. We can invert them in the same way. We can plot distance versus depth and color it by speed of sound. And then we can use that to look at changes over time. And this is where it starts to get really cool. We can now, instead of just concentrating on the strain that's occurring at the surface, we can look into the hill, look into the earthen structure, and go meters down by doing nothing more than just recording data and processing it the right way continuously. We can look 10 meters to tens of meters into the hillside and look at how the speed of sound changes over time. We can cut it in any direction we wish. We can look up and down, we can look across. But the key part comes when we start to look at changes and correlate them to other sensors. And that's what we've been doing at this location. So we talked about the ERT, the electrical resistance tomography earlier. What that is used is to establish this parameter called the gravimetric moisture content. Let's just call it the moisture content for today. And we talked earlier about there was this critical point, 45%, when the hill starts to get unstable and collapses. What the ERT sensors will produce is this sort of fractal-like pattern in the background. We're now looking at a slice through the middle of the hill from side on, and we're looking at how this has changed. Has it reduced in soil, in moisture content? Has it increased? We can then try and correlate that to what we're looking at from our velocity measurements, again, taking the same delta over time. And what's positive is that we see broadly for the top depth of soil here, things do align very well. The changes in the ERT producing this decrease correspond to this sort of negative change in velocity that we see. Sorry, there's positive change in velocity. We switched our axes around to get the colors to match. With an area in the middle, the flip sign, and then an area at the bottom which flips again slightly. And we see that corresponds to what's being pulled out of the electrical resistance tool to tell us about the nature of the soil. So this is really quite promising. Putting it back into a plan view where we can look a little bit easier. There again is the moisture content compared to our velocity change in the soil on now in a 2D slice near to the surface. And again, the behavior shows an incredibly good match. So what we are suggesting at this point from this sort of quite academic measurement is you've got a tool in the fiber optics to not only dynamically look at the strain and temperature, but also to start looking into the structure, looking into the moisture content, and trying to establish from that something about the physical nature of the soil itself. As I mentioned, if you know the density everywhere, you can then move from this to bring the stiffness out. And if you're starting to look at changes in the stiffness, let's say you've got a tailing dam, for example, if you're looking at the stiffness of that and seeing that change deep into the dam, you might want to investigate further. And that's typical of where this could be used. Earthen structures such as tailing dams, levees, reservoirs, etc. And what's nice about the approach to the technology is it can be adapted depending on your needs. You know, it is just burying a single fiber optic cable in the soil. If you just bury one through the top of the dam, you can look into that, looking around with some polar symmetry. If you want to do a little bit more, if you want more precision, more detail, you want to take different cross sections, you can deploy your fiber in different ways. If you want to look vertically through it, put it into boreholes and monitor the phreatic surface, look at where the water table is coming up. The access to the strain, the temperature, and this passive seismic approach at all points makes it a really powerful technique. So that's the sort of background that's leading us into these new applications. And we started with the strain and temperature, and now we're piling on the passive seismic on top. What I'm going to look at for the remaining 10-15 minutes of the talk is in a couple of recent industrial applications, which have been a little bit simpler, as you'd expect, where we're taking some of our conventional acoustic work and tying that into the strain and temperature. So we'll look at an example of temperature, we'll look at an example of strain, and then we'll see where that's taken us. So these are recent industrial projects. So the first one is pipeline thermal-based leak detection. So the situation here is that we had a pipeline operator who were originally using a DTS, but it wasn't giving us quite the temporal or measurement resolution that they particularly wanted. It wasn't giving them enough information. Their fiber optic cable was a dry powder filmed, which is not the best for DAS. Please steer away from dry powder cables, but we can have a look at it. But it would be particularly good for temperature-based monitoring. So the goal here was to deploy our system on the pipeline to perform pipeline leak detection and look at how best we could do it. Could we extract some acoustics, or could we extract the temperature information, or better still, can we do a bit of both? So this is the acoustic trace, just looking through a typical frequency range, 20 to 200 hertz, looking along the length of the pipeline, looking over time. This is our acoustic waterfall. And the immediate sort of observation from this is there's not a lot of activity going on. Normally we'll see cars, vehicles, people, etc. There's going to be some activity, and there's not a lot here. There's a little bit down here. You can see there's something quite large. This is actually a thunderclap. Both of these are thunderclaps. That one's quite far off. You can tell that by the shape of the curve. This one's a little bit closer, a lightning strike, but it's really quiet. So, you know, in my mind, that doesn't hold out much hope for doing leak detection using acoustics. Signals from inside the pipe do travel out and into this not very good cable. This is a pig that's passing, creating this negative pressure wave, which is now a very nice recognized leak detection technique with fibers in the latest update of API 1130. Well done to the team who got all that work done. And here we're detecting it, and we are picking up a negative pressure pulse. But you can see this is getting fainter and fainter the further you go down the pipe, and there's dropouts, stopping and starting. It's okay, it's okay. It's useful as one element of leak detection. Maybe we wouldn't want to rely on it for the whole of the pipeline length because there's just not enough signal. Normally, the passage of a pig would light this up, and it would be very obvious what's going on. So what about temperature then? What can we do with that? We've got all those acoustics going on. We're running our acoustic leak detection as best as we can. Will temperature show us something different? So keeping in mind that if you had a DTS on there before, you're having to average over time in order to get to a decent thermal resolution. If you want to get down to sort of sub-degree resolution, you're going to have to be averaging over tens of minutes, maybe longer. Here, from my first slides, we're talking about millikelvin and below resolution every second. So what we were able to see in looking at this is the very marginal differences in temperature in the product as it enters the pipeline and then flows along. And you see it does align to the background as it moves further, or some of that is just the quality of the signal. But what we're actually looking at here, the scale of this is 0.2 millikelvin, a thousandth of a degree per second. So changes that are really, really small, looking at them over the course of about 12 hours or so. And this is just looking at a thermal product moving down the pipeline. So changes in the temperature that are a fraction of a degree between the product and the ambient temperature, which is natural. You'll always have that. We're able to pick out and follow down the pipeline as the cable moves. Covers about 26 kilometers in 5 hours, about 1.5 meters per second. That's kind of what we'd expect. You see some dropouts in the data. We think that's caused by sometimes the fiber is pretty close to the wall of the pipeline, maybe touching it, and other times it isn't, and you lose that sort of thermal conductivity. But this offers, another axis to lean on for doing this sort of work. Similarly, we see some diurnal variation going on. It is quite deep, so that isn't going to be much, and it's going to be an antiphase to the variation that we see at the surface. And so again, all this encompassed within about plus or minus 0.2 degrees or so. It's really small numbers. But we regularly see this sort of thermal move out of the product through the pipeline. So this holds out some hope of a mixed and integrated approach using temperature from the same instrument as we're getting the acoustics. And here's just a short speeded up video running about 4 times real time, looking at a scale of plus or minus half a degree, and looking at these thermal pulses essentially move down the fiber over time. So heating and then cooling, and tracking the movement of that at that sort of 1.5 meters per second. Now the goal here isn't flow monitoring, although it's clearly pointing to evidence of flow, which could perhaps be useful. But the goal is trying to offer the clients an alternative mechanism to detect the presence of a leak in the pipeline. So here, with using this sort of mixture of negative pressure pulse where we can, combined with this very sensitive, very high spatial and temporal resolution, temporal and temperature, to be able to identify leaking product coming out of the pipeline, we think that there may well just be the chance to produce what the client is looking for in terms of that operating knowledge of how the temperature is progressing through the day. Second industrial example is where we're looking at strain. Again, this is on a pipeline. So here we have a gas pipeline operator. The nature of the ground he's operating in is concerned about sinkholes and or subsidence that might cause damage to the pipeline. And essentially the job is to perform our normal right-of-way acoustic protection, leak prevention, that is, and at the same time as trying to give some early advance of notice of changes that are occurring, to be able to potentially identify problematic areas, essentially an all-in-one capability. Whereas in the previous case, that was just using a powder-filled loose tube. In this case, we're using our Proteus 7. It's actually in a conduit in this case. Be better for it to be direct buried. You'll get a better registration of strain outside to strain in the fiber rather than a fiber rattling around in a conduit. But as you'll see, the results are still pretty good. So here we're doing 2 things. We're traveling up the fiber, up on one fiber, and then we're traveling down on the other in exactly the same way as we talked about at the beginning. Running up on the loose tube, running down on the tight buffer. The acoustics look pretty similar. If I get my glasses on and look closely, I would say that the sensitivity, or rather the signal strength, is slightly better on the right-hand side than the left-hand side, but they're both pretty good. They're both sensitive to acoustics. We see vehicles. There's an area with a bridge and a railway. That's trains crossing, so we don't see it for very long. But we can use that low frequency temperature element and separate the left from the right to also look at strain. So we're happily using our normal acoustic leak prevention technologies in this case. Here you can see very nice acoustic signatures passing into the soil, which this also then holds out a really good hope for doing passive seismic work on this later in the project to look down into the soil. It's much better if we can look down at situations that are starting to develop before we see them at the surface. That's the next step. Maybe that'll be my next talk. But for this one, what we were interested in is looking at the strain. So here we've looked at the strain as it's evolved over the sort of 7 or so weeks from the start of the project, plus or minus about 100 microstrains, which is pretty small, a reasonable number. It's a big signal for us, and looking at what's happening along the fiber. And there's a couple of areas that interested us. There's one area where there's a lot of strain change that's going on. That's this area through the bridge, going under a river and under a road. There's a lot going on in this little section. And then here we find there's another area where there's a significant bit of strain. So we can look in a little bit more detail at that. And so here we've got this little colored caterpillar. We can see that strain is going up and it's going down. It's changing along this section. It's quite a dynamic area. And so to make good use of that for static strain monitoring, you want to trend that over a long period of time and take out these sort of small temporal variations. This area here, though, this has got a slightly different pattern. What we saw, and this is quite a new pipeline, we were on it just shortly after completion, and what we saw was this upwards trend. There's a downwards trend before it and an upwards trend after it, but essentially a bit of compression and a large bit of tension on the fiber. When I say large, 100 microstrains, which is 100 parts 10 to the 6. So it's nowhere near danger levels for the pipeline. But and bear in mind, we're only measuring what's going on in the fiber. But nonetheless, something is happening here. And so this is looking at that evolving over an extended period of time. There's about a 50-meter section here with this 230 microstrains total increase, which if you do the physics, which you can always go back to the physics, it equates to about a centimeter of movement. So that is important over a sort of 33-day period. And there's the overall strain being tracked since we started monitoring. And when we go to the site, what we actually find from this is the ground is actually sunk in this area over a 2-week period, looking to be about 2 feet deep, maybe 7 meters across. And so that is something that's significant that the customer would want to know about. We think in this case, it's not related to sinkholes or damage to the pipeline. There's some issues with burial in this section, but nonetheless, it requires a little bit of attention. The reason I'm showing it is trying to sort of give you an illustration here of the potential sensitivity of these techniques. So it's a really good sort of visual illustration. So what I've shown you in these last few slides is how we can combine strain, temperature, and acoustics for different purposes. You have live acoustics for right now monitoring, situational awareness, with the temperature or strain giving us some information about the situation of the asset, the long-term situation. And then in the earlier part of the talk, we looked at the bringing in the passive seismics, which I see very much as going to be a really important tool for the future when the structure of the deeper asset, looking away from the fiber, is going to start to become important. But just to quickly round up differences in these techniques. So I've talked a lot about Rayleigh GTS and Rayleigh DSS. It's a different way of expressing distributed fiber sensing, DFS. I sometimes use distributed Rayleigh sensing, DRS. The traditional acronyms have always been DTS, and that's always been a Raman approach. That's a different backscatter technology. Go back to my previous talk if you want to learn more. DSS, distributed strain sensing, well, that's historically been the remit of BRIOAM. And what I don't want to do in this talk is knock any of those, because they're great techniques and we would use them ourselves as well. They're great for lots of different purposes. We're looking at large strains developing over time. If it was Holland's Hill, DSTS would give you a similar view of that long horizon, those month-long trends of large strain. Wouldn't be able to go down and look at the high temporal resolution stuff. Equally, both Raman and Briowan are signature based. What do I mean by that? What I mean is they're not working on the same backscatter as us. They're working on another measurement that comes out that is related to temperature. So I can calibrate my cable for a Raman shift or for a Briowan shift. I can record my measurement and see what that shift is along the cable. I can then pack up my instrument, go away, go and do some other jobs, come back in 6 months, record my shift, and know what the new temperature profile is across the cable. My techniques with Rayleigh that I've been talking about here, they're more of an always on. You know, if you're getting the acoustics, they allow you to get the strain and temperature at the same time. But they're an always on monitoring. If I go away, I'm back starting at 0 with no information other than the last bit of information I had. So there's some changes, and there's different scopes and different application areas that each of these might be useful. The real benefit that comes out of the approach I've been describing today is that it's a real-time, dynamic, and highly sensitive measurement. It doesn't require any averaging. The cable response is the same. You know, Briowan, they're coupled to temperature and strain in the same way, and you need a cable to separate out the two. Or there are some newer advanced techniques coming, whereas Raman is purely a temperature-based effect. So you've got these three classes of instruments, each with different sort of application areas, different niches that they all fit into. But if you're needing acoustics, you might benefit from the temperature and strain at the same time. If you're interested in dynamic situations, Rayleigh would be the way to go. If you're interested in the smallest signals, the smallest strains, Rayleigh's about the only way to go. And if you're interested in looking deeper into the structure with the seismic, that's very much an acoustic process. So you're going to need an acoustic-based system. But what I'm trying to do is pull all that into one unit. So as customers, you only have to buy the one unit. So what have we done here? Strain, temperature, and acoustics from a single device. I think that's tremendously exciting. It offers cost savings to the customer, offers complexity reductions out in the field, out of where the kit is located, in the data processing. Everything coming from one data stream makes an awful lot of sense. We can get hung up on nomenclature and acronyms. We just have to, I think, probe a little bit deeper into the nature of the measurements. What's the temporal resolution? What's the spatial resolution? What's the sensitivity? Can you do acoustics at the same time? These are all good questions for someone procuring systems to ask. So that brings me to the conclusion of my talk. I think I've really enjoyed getting these ideas out to FOSA yet again, and I will now hand over to Mark for questions from the audience. Mark.
Well, thank you very much, Chris. And to ask a question, there's obviously a text box, at least on the right, that you can share some queries with. I just wanted to kind of kick off with one that we have, which is, could you kind of elaborate on the benchmarks as we improve sensitivity using, using strain and temperature combined with acoustics? So what benchmarks can people use to kind of track how these improvements have improved the information that they're getting?
Yeah, so that is, I am aware that, as I was talking through this, there's a potential for, some confusion in terms of acronyms. I think FOSA are very helpful in that we publish a lot of information to help new adopters try to understand technologies. There's a lot of white page briefing papers that are available on the FOSA website. And we also go into individual applications, publishing application guides, which help try and sort of demystify where you would deploy individual technologies. Some of the key things that you can do, though, as a procurement official, I think, is to think about what is the nature of the measurement that you require. Now, quite often it's less about the measurement and it's more about the job that it's doing. So if you're trying to do leak detection on a pipeline, for example, but you should be able to convey the type of measurement that you're looking for, how often it is to be updated, and how you can prove that as a vendor that your system is able to do these things. And so, you know, those sort of benchmark measurements of looking at the responsiveness of your overall system, which will be your interrogator and the cable, to strain, how well calibrated they are, what's the response over time, for example, what length of averaging you require, will all help for procurement purposes. If that was how the question was organized.
That's very helpful. And so the next question is, I guess, a potential or perhaps a use case that's under consideration. Can near surface moisture and velocity, again, DAS, temperature, strain, monitoring apply in agriculture?
So this is an interesting idea. Yeah, so what I'm particularly have been floating around the back of my mind for a little while now is sort of vertical city farms, you know, non-traditional agriculture that require, you know, pinpoint monitoring of soil conditions. If you were able, for example, the fiber optic sensor running through those to look at the moisture content, could you use that in metering in your farms? That, I think, is something that's quite exciting for the future. The passive seismic stuff, I mean, we've tended to concentrate with that. We found that, you know, I talked about some of the limitations in terms of the frequency representation of the passive output, leading us to look a little bit deeper, maybe not just the surface layer. The temperature and strain are very, very, you know, dependent on the surface layer, and that's kind of one of the key differences. You know, temperature and strain, you're measuring it where the fiber is. Passive seismic, you're looking into the volume of the soil that you're interested in, and so they'll give you different answers depending on how you use them. But if you're interested in very, you know, high temporal fidelity of temperature measurements, for example, and being able to look at them as an analog to soil saturation, then that potentially could indeed help. I've got to say, we've never done any agricultural projects thus far, and in FOSA, I don't think we have a published guide on the topic.
Well, thank you. So the next question probably comes under the category of a frequently asked question across webinars, but since it's one that we probably should address. Could you elaborate on how optical cable is installed on the pipeline project to allow for distributed strain measurement?
Yeah, so I did touch on that one. In the second project where we looked at strain, we have a Proteus 7 cable, which I outlined the structure of that earlier in the presentation, and that's sitting within a conduit. So a conduit has been buried alongside the pipeline, and that's pretty common because it does allow a break in the operations. If you don't put in a conduit, you're going to drop your fiber onto the soil, and you've got someone there trying to splice it at the same time as they're trying to cover the pipeline, and one gets in the way of the other. The conduit type process can help alleviate some of those complications. And again, I suppose that we got some publications on this. So in this case, a conduit is laid alongside the pipeline. Fiber, the cable, is then blown through the conduit at a later date, coming out into handholds, spliced together, and then the end, and we only require access to one end, is attached to the interrogator. It really is a very simple process. As I mentioned, if you're after the finest resolution on strain, you're probably not going to get it because the cable does have some freedom of movement in a conduit. But in this case, we were able to still deliver very high precision measurements of strain. That's shallow depression of the soil coming from a cable that's slopping about within a conduit.
So next, and I think probably the last question is, after separation of temperature and strain, can we observe solid tide and its variation?
Solid tide was that?
Yes, solid tide and its variation.
I'm not sure if I understand the terminology, but I'm guessing you're talking about the physical structure of the soil there. Yeah. So at the moment, what I've shown you is extracting sound speed of sound, and how that has some granularity within the structure that we're observing. So you would expect to see layers, for example, dependent on the compression or dependent on the nature of the soil. You'd expect to see boundaries. So that's where we're first starting, because it's a little bit more accessible. There's a lot of processing that has to happen to get that, but we're doing that on projects, live 24/7. The next step beyond that is inverting from speed of sound back to the properties of the soil. Now, as in the stiffness. You can do that the hard way if you've got some density measurements, and so you put the two together and you can get back to it. But you're going to need something like an ERT array to be able to get the moisture content. You're going to need to have done some lab calibration of samples, and that's all starting to sound like hard work. Speed of sound, remember, is a product of density and stiffness. So there are mathematical techniques coming out of universities right now that have another layer of inversion. So we initially collected the frequency data, we then invert to speed of sound, we can invert again to soil properties, but I think that's coming. That's the subject of a future talk. So at the moment, you can still tell a lot about what's changing and about the distribution of the speed of sounds. They'll tell you a lot about what's going on underneath the fiber and into the earthen structure. And doing these change plots over time are really important to telling you how things are changing and modifying. Are they changing in the same place, for example? Or is one section changing its speed of sound more than the rest? And if so, why? Those are really key questions that we can help influence the answers with today and help with known problems. The next level beyond that is then starting to look at the significance of that through stiffness. That's a little way away yet. That's for a future talk.
Well, thank you. I'm afraid we're at the top of the hour now, but thank you for a very helpful presentation, very informative presentation. And I will answer one other question, which is the availability of the presentation. As are all our webinars from FOSA, it is available on our YouTube channel, of which there's a great deal of content. We kind of encourage folks to reach out to take a look at, or alternatively, Chris's email is available there, and I know Chris is available for more specific follow-up. So thank you very much, Chris, as always, and that concludes this webinar.
Thank you, Mark. Thank you, everyone, for paying attention.